So today we are going to talk about transformation operators, and we are going to prove this theorem that, let's say we have two sets of base gets and both are satisfying this orthonormality and completeness, then there exists a unitary operator such that I can go from B to A or A to B in this manner. I apply the unitary operator on the whole states, all gets, get B in similar fashion. Now this is the most important part. What does unitary mean? Unitary means that U is identity, but also U this is also identity. So these both must be satisfied in order for U to be a unitary operator or a unitary transformation. Now let's say we have the Cartesian coordinate system like x, y, z. I can always go from this to some, let's say, spherical coordinate system. But how do I go from Cartesian to the spherical coordinate system? So we always have some sort of transformation. There's always a matrix and some components. In similar fashion, let's say we have two incompatible observables. And their eigengets. Let's say these eigengets, they span the entire space, the entire state space or the entire ket space. And my interest is how can I go from one ket to another ket or vice versa. That is what our interest is. Just like this kind of transformations that we do in real space. Now we are interested in the arbitrary abstract ket space. So how do we go from that? So the U will take me from A to B. So what does my hunch tell me? Let's say what can be the structure of this? Let's say it looks like this. This is outer product. So my demand is this, that if I apply U on some A, I should get B. So let's try to see. I am U on some state. This will give me Dirac delta, Kronecker delta. Kronecker delta applied with the summation, kill the summation, and this will give me what? Will give me L. And this is what we wanted. So this is the structure of it. We also have certain demand like this, and integer U should always be an identity operator. So, is a dagger operation, so I will just reverse this order. It's equivalent to doing the complex conjugate. Reverse this order. A will come here, B will go there. Right, this will be chronopedata. This will become 1. I will get 1. One of the sum will be killed by this. So I keep the k. AK, AK. So it's nothing but the identity relation. Yes. So this is also satisfied. Now the next goal is to find the transformation matrix. So how would the transformation operator U would look like in the old basis? Know that if I want to represent some operator U in matrix form, I just sandwich it between the, let's say, L. You know that U operator AL will give you B. So this is a number. This is called transformation matrix. Say we have some arbitrary code alpha. Then this is the expansion coefficient in old basis. The goal is that how do I find such expansion coefficients in the new basis? what do we do? So when I apply U on B, it gives me U on A, it gives me B. But if I apply Mendeleev on A, it gives me the break order orders. I can insert identity here. Exploit this identity by writing in the basis L. This is old matrix, this is old expansion coefficients. Just multiplying them together gives me new expansion coefficients. So now the next thing is that what is the relationship between the old and new elements of some observer? So let's say the observable is X, and how can I write in a new basis? And I'm going to exploit the identity on both sides of old basis to get some relation between old and new. So we exploit identity here and here. Now I also know that this can be transformed like this in diagram. Same goes for here. So we use that. multiply u on some al and I get bm. This is the new matrix representation, in matrix representation of some observable x in new basis, and this is the same observable in old basis with multiplied by u dagger and u. And this is a very famous transformation. Let's say I define this like some x prime matrix. This is some u dagger. This is x. This is u. And this is called this relation is called the similarity transformation. It is very well-known result in mathematics and linear algebra and for the vector algebra stuff. So we did not even intend to reach to this result, but somehow using only the relationship of completeness, we reached this result. Since we have done the similarity transformation, let's try to prove some small results. What is trace of x is sum of all diagonal elements. How can we write in the bracket notation? It's just the same as the main size. We're going to use some trick here. It's dagger u. We can use this because there's identity here, identity here. So it's all about exploiting the identity in the end. And you know that this is going to give me B. This is nothing but similarity transformation. X prime. Change this. This is nothing but the interesting property that in the old and new basis of some observable x, the trace does not change when they are related, when the bases are related by some kind of unitary transformation. So it's one tiny thing. This is ux u dagger and not what we have is u dagger. If I do the dagger, this will swap. But these are observables, and we know that observables are Commission operator. So for them, x diagonal is same as x. So by the same result, x prime diagonal will also be same. X prime because x diagonal is x. So now we know one thing, that if trace is asked in this manner for any of the eigenbases or anything, we just sandwich it between two same cats, sum it over. That is what it is. It is summation of all the diagonal elements. What do we mean by diagonal elements? The sum over this same cats. This is going to kill this sum, and in return we will get this. So this is an interesting result, that if I take the trace of this old and new eigenbases, in return I will just get the inner product.